All right, so we're in section 2.3 now. We're dealing with linear equations. And just a reminder, chapter 2 is all about first order equations. And linear equations can come in any order. We can have nth order linear equations. The method that we're talking about for solving these guys is strictly for the first order case, which is why it shows up in chapter 2. So just as a reminder, a first order linear equation is a differential equation that takes this form. Some function of x times dy dx plus some potentially other function of x times y equals a function of x. And in order to come up with a solution method for this, we're going to put this in a slightly different form. We're going to divide everything by this a1 of x right here so that this dy dx has no coefficient on it. If I divide everything by that function of x, even though I could write, for example, this coefficient as a0 over a1, I'm going to just go with a simpler name and call it p of x. Why? This g of x is being divided by another function of x, producing another function of x. I'm going to call that f of x. So any linear equation, after dividing by this, let's call it leading coefficient, can be put into this form. Okay, and that's the form that we need it to be in to do what we're going to do in this section. Now, sometimes, depending on how this thing looks, you may have a separable equation, and you can use the method from 2.2, separation of variables, to solve that. But oftentimes that's not the case, and we don't have the option of separation of variables, so we have to take a different approach. Now, the approach we're going to take is going to utilize the product rule from calculus. Now, if you take a look at the left-hand side of this equation here, and if you really think about it, it has some resemblance to the product rule from calculus. So as a reminder, if you have a product of functions uv, the derivative of that would be uv prime plus u prime v. Now focus on just the v here for a second. First of all, we have two terms showing up on the left-hand side of this identity here, this equation. One of the terms has the derivative of the function v, and the other term has the function v itself. Now compare that v to the y that's showing up here. We have two terms again on the left-hand side of this equation. One of the terms has the derivative of y. The other term involves just the y. So it doesn't exactly match up with the product rule, but it has some similarities that we might be able to utilize. So the trick to what we're going to be doing in this section is we are going to try and force this left-hand side to fit with the left-hand side here of our product rule, and we do that by multiplying by some function mu of x. So if I think of some unknown function, and it is a specific function, but we're going to figure out how to find what it looks like later or in a little bit. Right now, we're just going to think of it as an unknown function, mu of x. If I multiply both sides of this equation by mu of x, I get this. Okay? Now, I've highlighted a couple of things in red here. And the reason for that is because these red functions showing up here would correspond to the u and the u prime in my product rule. Remember, I'm thinking of the v and the v prime as taking the place of the y and the dy dx here. So if this left-hand side is to look like the left-hand side of our product rule up here, then this function here, once I take its derivative, should turn into this function here. Again, this I'm thinking of as u, this red part here I'm thinking of as u prime. So again, that is to say that mu prime of x, the derivative of this, should equal mu of x times that p of x function that we would have known from our linear equation. The goal here is to figure out what mu of x looks like. I'm trying to solve for mu of x. If I divided both sides by mu of x, so I got mu prime over mu like that, and then integrate both sides, notice I get that down here. This left-hand side takes a familiar form from calculus. The antiderivative of this would be the natural log of the absolute value of mu of x. So that integral evaluates to this. Now, I don't know what p of x is explicitly because we're talking about a general linear equation up there. In a specific example, we will know p of x, but for now, I can't evaluate this integral directly. But I do know that after doing the integration on both sides, I will pick up some constant of integration in that process. So I'm writing that here, plus c1, and here it is again. If I wanted to solve for mu of x, I would start by doing e to the power of both sides to cancel out that natural log. That gives me the absolute value of mu of x equals e to the power of this thing, that integral of p of x dx plus c1. Using an exponent property, I can split this into a product of two exponentials, e to that integral times e to the constant of integration, c1. Now, because c1 is just an arbitrary constant, e to the power of c1 is yet again some arbitrary constant. Okay? So for that reason, I'm just going to call that c. E to the power of c1, just to keep things simplified, or simple, I'm going to call that c, so I can rewrite this thing as c e to the power of that integral of p of x dx. Now, that c, as written, would be positive because it came from taking e to a power, and e to any power is going to be positive. But notice this absolute value here has not been dealt with yet. Normally, if you take an absolute value, or if you want to undo an absolute value on one side of an equation like this, all you need to do is drop the absolute value bars and then put a plus or minus on this side. But that plus or minus kind of gets absorbed into that constant. Plus or minus some arbitrary constant is just an arbitrary constant. So we can sort of ditch the absolute value bars and not really have any consequence. Therefore, mu of x is equal to this function here, c e to the power of the integral of p of x dx. That function is something that we call an integrating factor. We'll encounter another type of integrating factor, a related integrating factor, in the next section when we talk about exact equations. But basically, the purpose of an integrating factor is to take something like this, a differential equation, multiply by that integrating factor in such a way that it makes this side of the equation something that we can integrate directly. Okay, on its own, we may not be able to do that, but multiplying by this integrating factor helps us in that process. Now, if you were to go back to this guy right here, remember the entire purpose of going through this derivation was to make this left-hand side match with our product rule. So if I'm thinking of mu of x as my function u in the product rule up here, and if I'm thinking of y as the function v, then this whole left-hand side here is the same thing as the derivative of mu of x times y. That's doing that product rule in reverse, or up here. So I can rewrite that as d dx of mu of xy equals mu of x f of x. Okay? Now the next thing you would do from here is use the fundamental theorem of calculus and integrate both sides with respect to x, because what that's going to do is cancel the d dx here. Okay? And I describe that here, but I don't go any further with my explanation of that process. Your book does. I want to point something out because this is sort of a common theme in differential equations at this level. We talk about a lot of different solution methods for differential equations, and a lot of them go through, at the beginning of a section when we're talking about it, we go through a derivation much like this one. Oftentimes those derivations eventually end in a really complicated looking formula, right? Which, if you plug everything into that formula, it should solve your DE for you, that kind of a thing. But then once they go through that derivation in this book, almost always they tell you, whatever you do, don't use this formula. They say, it's not a good idea to try and memorize all of these really complicated formulas. It's actually better for you to go through the derivation yourself with each specific example and solve it that way. And I've looked through a lot of differential equations books, and typically at this introductory level, they all say that. They all go through this big, long derivation, get a complicated looking formula, and then they say, just whatever you do, don't use it. And it's kind of annoying, in my opinion, because they put a lot of work into something that they're then telling you not to use. So in my notes, I don't go the full way that the book does, because what the book does is it shows the integration happening here, and then it solves for y. The mu of x, they substitute this function in, and there's just a few extra steps to get this thing completely solved for y. Since we're not going to be using that formula anyways, I'd rather not go through all that extra derivation. I would prefer to do that in a specific example. So let's do that, okay? We're going to start by solving this linear differential equation, okay? Now, typically you would want to check and see if the dE that you're working with is separable, because you can approach it by, separating variables. That's generally an easier process. But because this equation is linear, I can also use the method that we just talked about. So key thing before we do anything else is to make sure that there's no coefficient on this dy dx, or to be a little bit more accurate, we want that coefficient to be 1. So you first have to divide by whatever your leading coefficient is if it's not already a 1. Let's do that first. That's going to give me dy dx plus 4y. I'm dividing by 3, so it becomes 4/3, okay? We have to have our dE in this form before we can start looking at our integrating factor. Okay, now coming back over here, when we use integrating factors to solve linear equations, in the examples that I do, I'm not going to walk through all of this derivation. The one thing that I am going to memorize is what this integrating factor looks like. Mu of x equals some constant c e to the power of that integral right there. And in fact, let's actually start by determining what p of x looks like. P of x comes from the coefficient on my y term. And here, the coefficient on my y term is the constant function 4. So the exponent on my exponential is going to look like the integral of 4 dx, which is equal to 4x. Now, normally I would say 4x plus c, right? But you're going to see a lot of constants of integration floating around in a process like this. And to minimize all that work, we want to minimize the amount of constants of integration that we end up using. So I'm actually just going to write 4x, not 4x plus c, and we're going to see that it actually doesn't matter. In that vein, I also want to note, where'd you go? Here we go. I want to note that our mu of x looks like c e to that power. But again, in the process of solving all this, we're going to pick up yet another constant of integration, and this c here is not going to, it's going to get absorbed into that. So it feels a little bit wrong to do this, but I'm going to just assume that c is equal to 1 to simplify things. That means that my integrating factor is going to be e to this power, e to the 4x. Okay, so notice even though we derived this in such a way that would have put a constant here, an arbitrary constant c, we're going to just call that 1 for this process. I'm multiplying everything here by e to the 4x. E to the 4x dy dx plus 4e to the 4x y equals 4/3 e to the 4x. Okay, now what was the point of doing that? Well, this left-hand side is now the result of taking the derivative of a product of two functions. This is the result of using the product rule, specifically on the function e to the 4x times y. So I'm using the product rule in reverse to consolidate this down into d dx of this simpler looking function. Nothing's happened to the right-hand side yet, so I get 4/3 e to the 4x. Okay, what I'd like to do now is integrate both sides of this, because that's going to cancel out the d dx right here. Notice now I have e to the 4x y equals, if I integrate this guy, I should put a dx in there, both sides. If I integrate this guy, I'm going to get 1/3 e to the 4x. And here's where I'll include my plus c. Okay, now prior to this, I would have had a c floating around in here, and the work that we're going to do to solve all of this, we're not going to need that extra constant of integration. So we're actually safe doing this. All right, the last thing that I would want to do is solve for y, because if I can get an explicit solution, that's ideal. So I can do that by multiplying both sides by e to the negative 4x to cancel that out. Notice that would give me y equals 1/3 plus c e to the negative 4x. Like that, okay? So what is that? That process wasn't too difficult. This is one of the easier linear equations to solve. Notice all of our coefficients were constants. We weren't working with more complicated functions of x as our coefficients or as our term here. It gets much more complicated than that, but this is a good place to start. One thing I want to point out about this solution here, remember a lot of the time in differential equations, we are interested in the long-term behavior of our solution. Now this is a family of solutions, a one-parameter family, because I have that constant here, that arbitrary constant. But regardless of what this arbitrary constant is, what is the long-term behavior of this function? In other words, what happens as x approaches infinity? Well, e to the negative 4x is going to approach 0 as x goes to infinity. And what that means is that the long-term behavior of this function y, if we look at the long-term behavior, this term is eventually going to become negligible. It's not going to make much impact on what y is equal to. This 1/3 is basically everything's going to approach 1/3, I should say. So for that reason, because this term sort of drops off in a sense in the long run, we call this term a transient term. And to be a little bit more specific, in the solution to a differential equation, anytime we have a term in that solution that goes to 0 as x goes to 0, or as your independent variable goes to 0, that term is called transient. You can kind of ignore it if you're only focusing on the long-term behavior of a function. Notice something else as well. This dE up here is actually an autonomous differential equation. Notice if I went over here, well, I was pointing it as off the screen. If I go over here to where I divided everything by 3, I could write this as dy dx equals 4/3 minus 4y. That's autonomous, right? There's no x showing up anywhere in that dE. And with autonomous differential equations, generally what we want to do is look for critical points. Well, what is a critical point of this? If I set 4/3 minus 4y equal to 0 and then solve for y, I get y equals 1/3. Y equals 1/3 is an equilibrium solution, right? So even though it didn't ask me to graph this, that means that at 1/3, I would have this equilibrium solution, which looks like a horizontal line. And then in addition to that, if I look at the long-term behavior of this function, remember we said that this transient term eventually drops off. So all of the solutions in this infinite family are going to approach 1/3 in the long run, right? That means that 1/3 there is an attractor. Remember those terms, attractor and repeller? It's asymptotically, this is an asymptotically stable critical point, that 1/3 there. So that's just to bring in some of the stuff we talked about in chapter 1. We're going to squeeze in one more example before ending this video, and then we'll do a couple more in the next video. This time, I want to solve this dE, y prime plus 4xy equals x cubed e to the x squared. And notice it's actually more than just a differential equation, it's an IVP. Y of 0 equals -1. In addition to solving this, we want to find the largest interval I over which that solution is defined. Okay, and remember that really kind of boils down to examining the domain of our solution. So y prime plus 4xy equals x cubed e to the x squared, that's already in the form that I want it to be, right? Because my derivative, my y prime here, already has a coefficient of 1, so I don't need to divide everything by 1. But what I do need to do is identify what my p of x is and integrate it. So my p of x here is 4x. We need to integrate that first. 4x dx, that's going to equal 2x squared. And remember, we ignore the plus c here. The arbitrary constant will make an appearance later on, and it would just be juggling a bunch of constants which all get combined anyways in the end. We don't bother with it here. 4x dx, its integral is 2x squared. This is going to be the thing that I put in my exponent for my e to that power in my integrating factor. So we're going to multiply everything up here by e to the 2x squared. That's going to look like e to the 2x squared y prime plus 4x e to the 2x squared y equals x cubed. Now notice I have an e to the x squared here already. If I multiply by e to the 2x squared, I can combine those and I get e to the 3x squared up there. Okay, the point of doing that, again, was so that this left-hand side looks like the result of the product rule. So I consolidate that down, and I write that this is equal to d dx of e to the 2x squared y. All right, and then on this side I have x cubed e to the 3x squared. This is the point where we want to integrate both sides, because that allows us to cancel that d dx right there. Squeeze a dx in. Okay, my left-hand side, what happens there? Well, I just get e to the 2x squared y. My right-hand side looks like I would need some kind of a u substitution. So let's attempt that. Typically, if an exponential function is involved, you want to start by considering what would happen if u was equal to that exponent. So I'm going to try that. U equals 3x squared, which means du is equal to 6x. Now, I have an x cubed term showing up here, and that third power is not matching the first power that I have here. However, if I were to multiply the u and du together, u du, I would get 18x cubed, which is pretty close to what I have here. Let's take this and multiply both sides by 1/18. I get 1/18 u du equals x cubed. This is the substitution I can make for my x cubed right here. Okay, so let's make our substitutions. That's going to look like the integral of, remember, this is u du, and this is e to the u. So I get u e to the u du after all of that. Okay, now this requires integration by parts, but it's probably the first integration by parts example you've ever seen. It's a fairly straightforward one. I'm just going to write the result of what we would get by doing the integration by parts, but it's a good idea for you to practice filling in those gaps if it's been a while since you've done this. Over here I have 2x. Oh, you know, one thing I did forget, actually. I forgot to put my 1/18 in there. I'm going to squeeze that in because I can bring that out of the integrand like that, or out of the integral. I have e to the 2x squared y equals 1/18. This is going to become u e to the u minus e to the u plus c. Okay? This is the result of doing integration by parts on this guy. And again, try working through that on your own. Make sure you're comfortable with the steps and you remember how integration by parts works. Okay, let's work with this a little bit. So remember, u is the same thing as 3x squared. So I can take my 3x squared here, substitute it for my u's, and I also see that I have a common factor of e to the u showing up. So I'm going to actually bring that out entirely. I have e to the 2x squared y equals 1/18. Remember, the e to the u, which is e to the 3x squared, is going to come out. That leaves me with u, which is 3x squared minus 1 plus c. Finally, I want to solve for y. So I multiply both sides by e to the negative 2x squared. That's going to give me y equals, simplifying here, I would get 1/18 e to the just x squared now, 3x squared minus 1, plus c e to the negative negative 2x squared. It's a sloppy 2. Okay? This is going to be my general solution. But remember, we were starting with an IVP here, and that means I need to substitute 0 for x, negative 1 for y, and use that to determine the value of my parameter c here. That way I can get a specific solution instead of this general solution. And I actually forgot to mention this up here. I gave this term up here. We're going to start calling these infinite families of solutions general solutions, because the process that we use to solve them basically gives us the entire family of solutions that are possible for a DE, with the possible exception of these little equilibrium solutions or singular solutions. So this is the general solution, but let's plug in our initial condition. So if I plug a 0 or negative 1 in for y, I'm going to get, let me do this. I'm going to say initial condition. That just means I'm plugging my initial condition in. Negative 1 equals, okay, I'm going to plug a 0 in for x. So this term would go to 1. I got 1/18. This whole thing would go to negative 1. So this becomes negative 1/18. And then this term right here is going to become c times 1, or just c. So plus c. That implies that c is equal to negative 17/18. That can be plugged in for the c here, so that my specific solution is 1/18 e to the x squared, 3x squared minus 1 minus 17/18 e to the negative 2x squared. Okay, notice that we have a transient term on this solution. Again, this extra term out here is going to very rapidly approach 0 as x goes to infinity. So we can apply that term here. That means in the long-term behavior of this thing, it's going to really just look like this function. It's going to very, very closely approximate this function, because this term becomes negligible after a while. We were also asked to find the largest interval over which the solution is defined. Looking at this function, I know from what I know about the exponential function and polynomials and things like that, this as a function is defined everywhere. So I can use as my interval the entire real line. There's no discontinuities to worry about anywhere. Okay? That's going to wrap it up for this first video.